Hi everyone, I'm Ishaan, and this summer I had the opportunity to work with Dr. Muching Chen and Dr. Vincent Wang on the Double B robot. Double B is a hybrid robot that combines both wheels and propellers, and the question we ask is a simple one. Can a robot like this learn to use both together efficiently without us telling it when to drive and when to fly? So let me show you how the platform is first. Two tilting propellers, two driven wheels, and six actuator channels in total. The whole thing is approximately 3 kilos. Now, the propellers tilt, and that matters more than it sounds because it means that thrust is not used just for flying, but the robot can also angle those props to push itself down into the ground for traction. And that is the detail that this whole project is built around because here's the problem. Stairs break both modes. If you drive, the wheels stall at step edges because ground drive simply cannot get over a discontinuity. And if you fly, it works, but you're lifting 3 kilos of robot to gain 3 centimeters of height, which is enormously wasteful. So, how do existing systems handle this? They hand design locomotion modes. A rule based mode decides when to switch between them. Each mode gets tuned separately. And the cost of all of this is that a mode you did not design is a mode that the robot does not know about and the robot does not use. And efficiency lives in the gap between these modes, which brings me to question, can efficient hybrid actuation emerge from learning alone without prescribing discrete locomotion modes? We make two contributions towards this. The first is an energy aware RL framework, which optimizes task success and real energy consumption at the same time across three different types of actuators. And the second is a stricter success metric, wherein the policy has to close in the XY proximity, gain the actual height, and stay stable all at the same time, which stops it from claiming a climb which it never really made. Training happens in Isaac Lab with 1024 environments in parallel using the off-policy algorithm TQC. Step heights grow from 3 to 9 centimeters as the policy improves, and that's the curriculum gating. But the line I'll point you to is the middle one. We penalize true electrical energy in joules from calibrated motor models, not just action magnitude, so that the policy is optimizing the thing we really care about. As you can see in the video, it pitches back and drives through rather than just flying over. Now, getting onto the real hardware, there were three important things that we tackled. System identification for a calibrated thrust curve because physics X has no aerodynamics of its own. We also domain randomize over mass, center of mass, friction, thrust, and pushes, and latency, which is also an important one, where one control step of observation delay is added, and plus the actuator lag. Put it all together, and those let us deploy to the real hardware zero shot without any fine tuning at all. So, how does the simulation look like? Green is wheels only, and it never succeeds because wheels stall at step edges. Orange is propellers only. It gets going early, but it plateaus around 30%. And look at the energy on the right. It climbs to about 6,000 joules. Blue is the hybrid policy. It passes 50%, and it does that around 1500 joules, which is 4 times lesser energy compared to propellers only, and also nearly double the success rate. As for the real robot, this is the accumulated energy over 3-second climb. Red is our policy, blue and green are the hand designed decoupled controllers. Our policy finishes at around 356 joules, and the successful baseline is 571, and that's a 38% less average power shown by the RL policy. Also notice the shape of the red curve. It's almost flat through phase 1 and 2. It's spending very little while approaching and climbing, and the other two burn energy the entire time. Here it is on the hardware with 3 phases: approach, climb, and stabilize. And what I find genuinely interesting is that nobody told it to pitch back and thrust upwards. That's the physics the hand designed controller encodes, whereas the policy found it on its own. Now, to be honest about the limits, climbing degrades beyond 5 centimeters on hardware. The propellers just aren't strong enough at that point, and curriculum is doing the real work here since reward shaping alone never finds a stable climbing behavior. Going forward, we want to test out the policy on taller and more irregular terrain, try out seeding the motion priors into the training pipeline so that rare behavior can emerge and the whole policy can converge faster as well, and also model the higher fidelity actuators better. I would like to thank DARD for sponsoring my stay here, and I would also like to express my gratitude towards Dr. Mujib Chow and Dr. Vincent Wang and all of the A Lab for supporting me during the last 3 months. I would also like to thank Rachel and Dr. Dolan for coordinating this program. Thank you.